Next up is Mando Hendricks, Ultraviolet Characteristics of Low-Albedo Class Asteroids.
Okay, thanks. Okay, so shifting gears a little bit from dynamics to surface composition. Okay, so this is some work that we've been doing looking at what we can glean from ultraviolet data of low-albedo class asteroids. And what I'm showing here are spectra of a series of low-albedo class asteroids from the 8-color survey. And so this is covering 0.3 to 0.6 microns. Most of these bodies tend to exhibit absorptions or an absorption near 3 microns, which can be used to study hydration and organics. And then aside from that, most of the spectral activity on these bodies happens into the UV. And so they all exhibit this UV absorption, which is a intervalence charge transfer due to ferric oxide, and comprises several mixed up absorptions in there. And it has been, a lot of these bodies also contain a 0.7 micron feature, which is also linked to hydration. And so some groups have looked at linking this UV absorption edge with that 0.7 micron feature, with the 3 micron feature, and what it might have to do with hydration and heating. And we still don't really understand any linkages there. So what we're trying to do is look at this spectral region and see what we can learn about the surface compositions of these bodies, since there are so few clues at longer wavelengths. So really what we're trying to do is push deeper into the UV even than the 8-color asteroid survey can give us, and use our knowledge of what is happening in the UV from what we've been studying over the past few years. And we're using IUE data mostly, which is the International Ultraviolet Explorer, which is basically the only source of data for C-complex asteroids right now. Okay, so we're intercomparing the UV spectra of these asteroids, and what we're doing right now is looking at how the spectra compare with groupings based on the 3 micron spectral shape, how they compare with taxonomic classifications, how they compare with lab data of carbonaceous chondrites, and also phyllosilicates and other candidate species. So that's where we're going with this talk. So here are our data sets. These are all of the bodies that we're looking at here. And as I said, we're focusing on IUE, but we're making composite spectra by combining IUE data with SMAS, 8-color, 24-color, and spectra from the Vilas and Sawyer suites of observations. So it's not a huge database, but it's what we have to work with, and we can look for trends. And here are our composite spectra of those asteroids, or at least most of them. We won't go through these. I know these are small, but they're composite spectra from 200 to 600 nanometers, and we're combining what data sets of each of these asteroids we have from those data sets. And so we're focusing on this region in here, looking at spectral trends, but also keeping in mind what's happening at longer wavelengths, trying to be mindful of that as well. Okay. So one thing we can do is consider the asteroid's 3 micron characteristics. For instance, Andy Rivkin and others have looked at these spectral shapes that come up. This is 3 microns out here, and shown that there's trends that are seen. Here's Themis, Ceres, and Pallas, and here are Themis, Ceres, and Pallas using SMAS data and 8-color data, and we see differences in this UV drop-off among these asteroids. And when you add in the IUE data, you can see that there are distinct differences, at least for Ceres and Pallas. We don't have IUE data for Themis. So what that difference means, we don't know yet, but it's one thing to keep in mind. Okay, now we can also look at this Some of the asteroids have what's called a Series-like 3-micron absorption. And for our data set, those bodies are Ceres, Hygeia, and Bamberga. And so here we're comparing Ceres and Hygeia, again in the 200 to 600 nanometer region, and Ceres and Bamberga. And Ceres is in the red for both. And there's a suggestion here. There's scatter in the data, but especially at the longer wavelengths of the IUE where things are not quite as noisy, there's a suggestion of somewhat shallower UV slopes for Hygeia and Bamberga compared with Ceres, which suggests that there's a difference in the UV slope among these Ceres-like asteroids, given their 3-micron shape. We can also look at those bodies that have what's called the sharp 3-micron feature. And I'm not showing you Polyxo. I'm not sure about the quality of those data in the IUE, but we have Davida, Alexandra, and Interamnia. And Rivkin also says that Pallas is one of these sharp 3-micron features. So here we're comparing with Pallas. Pallas is in red in these 3 plots compared with Alexandra, Davida, and Interamnia. And we can see that Davida and Alexandra look pretty similar to Pallas in this region here, but Interamnia is definitely different. Something different is going on with Interamnia. So again, within this group, characterized by their shape of their 3-micron feature, we see differences in the UV. We can also look at taxonomy. So the CH subclass is part of the C complex that has a 0.7 micron feature. And these all, and for our data set here, they are Zelinda, Chloris, and Daphne. And they all look pretty similar. Here we're just kind of comparing to Pallas as kind of a control, but they all look pretty similar. We can also compare within the CGH subclass, and this is a class that exhibits the 0.7 micron feature and also supposedly has a sharper, stronger UV absorption edge. I don't think I buy that based on our data set, so we might want to revisit that. Alexandra and Nemausa are both considered CGH, and they're definitely different, which is really interesting. Alexandra looks a lot like Pallas, but Nemausa is definitely different and seems to absorb at a longer wavelength than Pallas does. So again, differences even among a taxonomic subclass, telling us that we might want to revisit that. Okay, we can compare with carbonaceous meteorites, carbonaceous chondrites, at least a couple CI and CM meteorites as measured by Wagner et al. And published in 1987. Here we compare Pallas with Murchison and Orgay, just kind of as an example. And Pallas is in red, and Murchison and Orgay are in black and blue. And we see that the UV absorption edge on Pallas is much stronger. Really what's happening here is that the UV drop-off in the meteorites is happening at a longer wavelength. So Pallas stays flat until a shorter wavelength. The chondrites seem to drop off at closer to 500 or 600 nanometers, whereas Pallas and many of the other C-complex asteroids drop off at about 400. And here's Ceres, and Ceres is the one asteroid for which we do have HST STIS data in the low-albedo class. And the Ceres is in black and red here compared to Murchison and Orgay, and you can see that the UV drop-off on Ceres is much stronger and at a shorter wavelength than the meteorites. And we are attributing this to perhaps the presence of additional opaques on the surfaces of the asteroids, which could be weathering products. So they might mute the absorption down to a shorter wavelength. Okay, And interestingly, though, when we look at Murchison and Aurigae, now in black and cyan, and compare them to Pallas and Nemausa, Nemausa actually looks a lot like the chondrites. It drops off, as we mentioned already before, at a much longer wavelength than the other asteroids. So that's interesting. And then we can also compare with terrestrial phyllosilicates, such as those measured in the USGS lab and in Ed Clutis's publications. And these are a few of them are shown in black here compared to Nemausa and Pallas again. And again, similar to the chondrites, you can see that they have redder slopes in this spectral range, which means that their UV absorption edge, which is not obvious from this spectrum here. They do have a UV absorption edge, but it occurs in a much longer wavelength than the asteroids do. So again, we think that probably additional opaques, probably in the form of some weathering products, perhaps there's enough olivine on the surfaces of these C-complex asteroids to produce submicroscopic iron. Or perhaps it's a carbon, like an amorphous carbon that's produced as a weathering product that will subdue the absorption feature. So we're going to be looking into that. So to summarize, we are looking at these C-complex asteroids, getting as far into the UV as we can. We're comparing and considering what the 3-micron absorptions are like. For the Ceres-like absorption, there's a suggestion that Hygeia and Bamberga have shallower slopes than Ceres. So we see different characteristics in the UV and blue, even though there are similar characteristics at 3 microns. Sharp 3-micron absorptions, we see that interamnia is quite unique. And considering the CGH bodies, we see that they are definitely not similar in the UV. We see that Nemausa and Alexandra, at least, are very spectrally different. And we also see that CM and CI carbonaceous chondrites and phyllosilicates largely have UV absorption edge at much longer wavelengths than the C-complex asteroids that we're looking at. We need to do some spectral modeling of this, but we're attributing it right now to weathering products, creating opaques on the surfaces. So the bottom line, though, is that UV spectral shapes don't totally correlate with hydration. And so we think that the spectral shapes are rooted in some other property of the asteroid surfaces, composition or weathering. We are working on this as part of our new survey program, which is called TREX, and we'll be making some lab measurements that will hopefully support this work and help us understand what's going on these asteroids. So, thank you.
We have time for a couple questions.
Oh. I'm gonna go to I saw Umberto first, but you want me to go to her?
Yeah.
All right, there you go. There you go.
You didn't talk about it in this presentation, but previously you had showed some, I think, far UV data for Ceres that suggested the presence of carbon.
Yeah.
Now, is that consistent with all the data you showed here, or is that something completely different?
No, it could be very consistent, but Ceres is the only body that for which, low albedo class body, for which we've got data far enough into the UV to see that bump that we're attributing to graphitized carbon. I think it probably is there on other bodies, but we need the data.
Phaethon is related to Pallas. It's believed to be part of the Pallas family and it came close to the Earth. It'd be very interesting if we can get those ultraviolet spectra of Phaethon. The Japanese are planning a Destiny Plus. I don't know if they have an ultraviolet spectrograph. Plan.
They should carry one. I don't know if they're planning on it.
This is great. It's always wonderful to see more asteroid data. So it's right, when you spend enough years with enough asteroids, you know them all by name, right? So interamnia, there's some data that shows that sometimes it looks more like Ceres. in the 3 micron region. So it'd be interesting to compare to see
Okay.
if, you know, if it looks more like the Ceres Hygeia, Bamberka ones. And the mouse is
Okay.
interesting because it's has the deepest 3 micron band for anything for which we have good data.
Oh, so maybe that's even consistent with what we're seeing.
So yeah, so it'd be great
Yeah.
to kind of get, I think the future of all of this is getting,
Yeah.
you know, the UV and the 3 micron and the mid-IR. The people are all looking at this and get us all in the same room and go, you know,
Right.
yeah.
Cool.
Are we out of time?
Yeah. Okay. Thank you.
Okay, thanks.
Next